So here we have a 350 kilogram roller coaster. It starts from rest at point A, slides down a frictionless loop-the-looped. And then it says using conservation energy, calculate these different parts A, B, C, D, and E. If you need to, pause the video, read those parts. Alright, other than that, I'm going to get cracking. Part A wants us to find the speed at point B. So using conservation energy, because it is frictionless, aka conservative system here, because nothing is lost, or when I say nothing, no energy is lost. Mechanical energy at point A must equal to the mechanical energy at point B. While mechanical energy in this particular problem is composed of Ke and Pe, or Pe and Ke, doesn't really matter how you write it. I'm just going to write Pe plus Ke. So if you break up Me, you get Pe due to gravity plus Ke. That equals to Pe at point B plus the Ke at point B. But here I'm going to cross out Kea because it starts at rest, so there is no kinetic energy to start because the problem starts at rest. There is Pa because there is a height above the ground, which here in the diagram, this is 25 meters. At point B, if you look at the diagram correctly, point B, it is 3 meters off the ground, so there is a potential energy due to gravity. So hence, mgHb, hb being 3 meters, and then I broke up KEB into 1/2 mvb squared, because ultimately we're asked to find the speed at point B. So that's an indicator that you need to expand KEB and so that you have VB square. Okay. Here you could cancel mass out if you like, because there's a mass on the left, there's a mass on this term, there's mass on that term. So because m appears in every term, you could cancel it out. But for this particular part, since this is just part A, I'm just going to show you. You could, if you want to, just plug and chug. Okay. So I'm just going to do a plug and chug real quick. Here, mass is 350, H is G is 9.8, and then here's positive because we're just looking at a scalar quantity, because energy is a scalar quantity. HA being 25 because it's given in the diagram. M once again 350, G being 9.8, HB being 3 meters because the diagram says point B is 3 meters off the lowest point, the ground. And then 1/2 mvb squared, m being 350. So if you simplify on this calculator, on the left side of the equal sign, you get 85,750. 350 times 9.8 times 3 gives you 10,290. And then if you simplify 1/2 and 350, you get 175. And you still have to multiply that VB squared. Well, all we have to do is combine like terms now, or move the 10,290 to the left side, which makes it negative. And then the right side, 175 VB squared stays the same. So if you simplify this, take the difference, you should get about 75,460, and then the right side stays the same. Well, to get VB squared by itself, divide both sides by 175. So if you do that correctly, you should get about 431.2. And this is VB squared. But you notice you're not done yet. This is VB squared. The question asks you for the speed at point B. So to get VB by itself, take the square root of both sides. That will cancel out the exponent. And then on the left side, the square root of 431.2 will give you about 20.77 meters per second. And because it says speed, we don't need to include directions or anything. Okay. Other than that, let's do part B. Part B wants you to find the roller coaster's kinetic energy at point C. You notice here it says kinetic energy, not speed. So know when to break functions up, know when to leave them alone. Okay. And then part C asks us to find the roller coaster's speed at point D. All right. So let's go ahead and do part B. To do part B, I'm just going to set up conservation energy again, because the instruction here says use conservation energy, right, to calculate these things. So I'm going to set up mechanical energy at point A, which is equal to the mechanical energy at point C. So the energy that I have to start must be equal everywhere else. Okay. Once again, I'm going to break up MEA into two terms, PE due to gravity plus the kinetic energy, and then same with point C. But once again, because the problem starts at rest, KE cancels out. And here at point C is 16 meters off the ground. So watch my cursor. In the diagram here, it says from ground all the way up to E is 12, but then from E up to C is another 4. So 12 plus 4 is 16. So make sure you measure things correctly, and make sure you interpret diagrams correctly. Otherwise, you're going to take an L just because you're sloppy. All right. Other than that, you notice here in my work, I expand PEA into MGHA. I expand PEC into MHC. But I did not expand KEC. Why? Because it asks you to find kinetic energy. So I'm going to keep KE as is. I'm not going to break it up into 1/2 mv squared. All right. Other than that, plug and chug time. M is 350, G is 9.8, HA is 25, M is 350, G is 9.8, and then HC here, I highlighted, is 16. All right. So make sure you measure correctly. From ground all the way to point C is 12 plus 4, which is 16. So therefore, other than that, calculate the work time. Left side stays the same as the previous part, 85,750, because that's the mechanical energy at point A. And here we have 350 times 9.8 times 16. It will give you about 54,880. So to find KE at point C, the kinetic energy at point C, all I have to do is subtract 54,880 from both sides. So I'm just going to move it to the left side equal sign. So it was positive, now it becomes negative. And if you do that in your calculator, 85,750 minus 54,880 will give you about 30,870 joules. Okay, that is the answer to part B. All right, let's do the roller coaster speed at point D. Okay, well, to find the roller coaster speed at point D, once again, I'm going to set up my conservation energy. But here, I'm just going to skip the MEA and MED part. I'm just going to get straight to the second line. Mechanical energy is composed of PE plus KE. Well, I'm going to start at point A, and I want to go to D. So, as usual, for this problem, I'm going to cancel out KEA because it starts at 0. And I'm also going to cancel out PED for this part because if you look at the diagram, point D is at the lowest point. It's on the ground, so there's no height. Well, if there's no height, there's no PE. So this one, pretty straightforward. Well, PEA is expanded to equal to MGHA. Well, the kinetic energy function is 1/2 mv squared. Well, which v? V at point D. And that's what we're trying to find. But as you can see here, unlike the other parts, or unlike part A where I plug and chug, I'm actually going to go ahead and cancel out m out because m appears on both sides. So I'm going to go ahead and multiply both sides by 2. Ultimately, I'm trying to solve for VD squared, right? Or VD. But really, the first step is to get VD squared by itself. So I'm going to multiply both sides by 2. So I'm just going to move this 2 in the bottom to the left side, and that goes in the numerator. Hence, I have 2GHA. And now, to get VD by itself, I need to square root both sides. So squaring both sides makes this exponent 2 disappear on the right side. And there you go on the left side. So radical 2GH. Well, I can just plug it in. 2 stays the same. G is substitute with 9.8. HA is 25. And if you simplify this on your calculator, 2 times 9.8 times 25 gives you 490. And then the square root of 490 is about 22.1 meters per second. Okay. Other than that, that is the answer to part C. Okay. And then let's go ahead and do D. It says, how hard does it press on the or against the track at point D? Well, at this location here, the track, as the roller coaster comes up, okay, or excuse me, as the roller coaster makes this loop to loop and it comes down to point D, well, F of G is still acting on the cart. So here's my F of G, but there is a contact force that's exerted by the track onto the cart. And in this case, this is called F of N. Alright, the force exerted on the object by the surface is pointing upward. Well, for this particular location, it's pointing upward because, well, the track is here and perpendicular to the surface, which is x-axis here, is along the y-axis. But here I've drawn F of N a little bigger than F of G. Okay, as an object continually moves in a circle, its F of N and F of G are different. They're not equal. Actually, for this location, Fn must be a little bigger. Okay, so to do part D, I need to calculate Fn. How do I know to calculate Fn? Because this is how hard does it press against the track. Well, if the cart press against the track must push against the cart, which equal amount, just opposite in direction. So that's an indicator that it wants to find F of N, the contact force. Well, here, the centripetal force is just Fn minus F of G. And you take Fn, because it's pointing upward, minus F of G. Well, you subtract because F of G is pointing downward. So F of C is F of N minus F of G at the lowest point on the track. Well, the question is asking for F of N. So what I did was I broke F of C. F of C is mv squared over r. F of N I kept the same because that's what I'm ultimately trying to find. F of G I broke up into m times G. So to get F of N by itself, I'm going to move this negative F of G to the left side, which makes it positive. So as you can see here, I have pretty much everything. I have m. I know the radius is 6 because here in the diagram, the diameter of this track is 12, but I need the radius. So the radius would just be half of 12, which is just 6. All right, and then I know the answer to part D, or the velocity or the speed at D is calculated in the previous part, which is 22.1. So here in my work, mass is 350. The 22.1 I took from part C, because part C asks us to find the speed at part D. I want to square that. I want to divide it by r being 6, because once again, the diameter gives, the figures gives you the diameter of this track, or loop-to-loop. So half of the loop-to-loop would just be 6 meters, okay? And then M here is 350, and then G, once again, the negative sign is already taken care of for you in my work, so you just plug in a positive 9.8. Other than that, calculator work, if you punch all the stuff in, the first term will give you 28,490.6, and the second term, 350 times 9.8 is just 3,430. And you're going to add those two, and this is our answer, 25,060.6. Okay, so that is F of N, or the how hard it presses against the track. All right. Part E wants us to find the magnitude of the centripetal force at point E. Well, point E is at the top of the loop here, which is 12 meters off the ground. So to find the magnitude of the centripetal force, all I have to do is apply the centripetal force function. It wants us to find F of C. So F of C is equal to mv squared over r. Which v? The v at point E, because this is at point E. I know the mass, which is 350 kilograms. I know the r, which is 6 meters. The only thing I'm missing is VE, the speed at point E. So I'm just going to go ahead and set up conservation energy. Here, I'm going to start at point A. Once again, the kinetic energy at point A is 0 because I've been canceling that out of my previous work. So I'm just going to go ahead and just get to it. The energy to start is due to PE, which is mgha. At point E, it does have a PE because it is above the ground. And then here, we need to find VE because it is moving. So I'm going to cancel M out because M appears in each single term. And then I'm going to go ahead and move GHE to the left side because ultimately I'm trying to find VE squared. In this function here, I want to point out FC at point E is equal to MVE squared divided by 6. I need to know what VE squared is. Okay, so I'm going to do a couple steps here. I want to move the GHE to the left side, which makes it negative. But at the same time, in order to get VE squared by itself, I need to multiply both sides by 2. So I'm just going to move this 2 up there, but I need to put it around in parentheses. So you notice here in my work, the 2 went up to the top left. Here, you don't have to, but what I do is I factor out with G. There's a G in this term. There's also a G in this term. So I factor out with G. Again, you don't have to. I just like to, okay? So here, I have 2G times the parentheses HA minus HE, which is the change in height. Alright, other than that, I kept the right side as VE squared because I need VE squared. So here's where you don't want to like square root and then have to square it again. It's entirely up to you. I'm going to keep my VE squared because I need VE squared because the function for f of c needs V squared. Alright, you can just plug and chuck. 2 gets carried down. G here is 9.8. HA is 25. HE at this location, it is 12 meters because the diameter of this loop-the-loop is given as 12. Alright, other than that, you can simplify this on your calculator. If you take 2 times 9.8 and then 25 minus 12 is 13 times 13, you'll get about 254.8, and that is VE squared. I will not square root it here because I need VE squared. Okay, you can square root it and then square it again. It's up to you. But I'm just going to carry my work down. So therefore, I'm just going to plug and chuck. 350 gets carried down. VE squared is replaced with 254.8. And that's it. Once again, don't square it here because I'm leaving it as VE squared. And then divided by 6. And if you do this on your calculator, you'll get a value of about 14,863.33 newtons. Okay? Alright, other than that, I hope that helps. Stay nerdy. Don't be wild.